All right, we're back for another installment of programming up that forward-facing step problem. So last time I showed you how we loaded and looked at the results, and this time I thought we would increase the resolution just a bit and see how the results change. So the objective of this quick lecture is to do a higher resolution psi.m file and then compare the higher resolution. So I'm going to go up by 10 in both directions. So it's actually going up or increasing the computational domain by an order of 100, right? 10 on x, 10 on y. And then we'll just have a quick look at the solutions and compare them. Okay, so let's stow this and let's bring forward the... So over here in this window, I think we will have a look at the original M file. That's this guy right here. And in this window, this is like one of those cooking shows where I've already done all the work for you, and I just bring out the turkey. Here I've already coded up the higher resolution. All right, so let's look at it line by line. This is where we started before, right? And we did 40 iterations in the previous calculation. This time we're going to go up to 500 iterations. And then there's this I-skip in here, and I'll show you what that I-skip is later. But it's basically a way that we're going to speed up how fast the code runs. Now, here's where we started to loop through. This is like where I reinitialized or I initialized our variable psi. Set everything equal to -1, and it went from 10 to 6, right? So over here we're going from 100 to 60. And pretty much everything's the same aside from that, right? I mean, the boundary conditions now, instead of going from 1 to 6 over here, we're going from 1 to 60. So we just multiplied everything by 10. We're still confining the size, the values of psi between 0 and 5 from the floor to the ceiling of the computational domain. So we're doing that here and here. And then a little bit of trickeration with the inlet. I have to, in order to normalize this was kind of a simple equation, right? When we had the inlet, we wanted the stream function just to go from 0 at the floor to 5 at the ceiling. So I use this little equation here, j minus 1, where j went from 2 to 6. And over on this end, I'm going where j goes from 1 to 60. And so I'm getting this equation that j minus 1 will put that to 0, and then when I get to a value of 60, that'll be j minus 1, that'll be 59 times 5 divided by 59, so we'll end up with 5 for that value of psi at the top of the boundary. Let's see, everything else is pretty much the same, right? We go through and we loop, and we loop in front of the step, and then we loop behind this or above the step. And the only thing that's different is this I-skip that I added. And so, as I mentioned before, the slowest thing the computer does is do I/O, either writing to screen or writing to file. So I don't want to write every data file to file, every iteration to file. That would be a lot, and it would slow us down. So I'd like to skip, right? And so we set this value of skip to 50. So the way this will work is we'll only get every 50th iteration. So we'll get the first one right here. We'll get 0, and then we'll get every 50th. Now let me show you how this logic works. It's right here. So this is an if statement in Matlab or Octave. So it says if n divided by I skip is equal to the integer value of n divided by I skip. And so they are different, right? There's a difference between real math and integer math. So for example, if I'm saying that if n is equal to 75, right, and then I ask what's the value of n divided by 50, oh, I got to be in octave. N is equal to 75, n divided by 50, right? It's 1.5. But if I ask for the integer value of that, the int16, that's a 16-bit integer, it's equal to 1. You see that? So there's a difference. So the only time that this statement is going to be true is when n is an integer multiple of I skip. And so when it is true, then it goes into the file, or it does this portion of the if statement. It does the interior portion, and it writes the file. Sorry, it builds the string for the file, and then it writes it. So you can see that it's going to just give us every 50th iteration. All right, well, let me make sure I'm in the right directory here. Now let's change directories to the larger domain. So you can see even within Octave or Matlab that these commands, these pwd commands and change directory commands, those are all based on Linux, right? So all of these interpreted languages are Linux-like languages. Okay, so I got this here, and I can go ahead and run this. Now this is going to take some time. So why don't I just kind of wait this out. Let's see here. So you can see right here, we've got the first data file. We've got the 50th. Oh darn, I double clicked on it. And we're at 100. And we're going to do 500 iterations. So this is going to take a few minutes. So we'll just wait. All right, so good old Matlab. All right, so it's finally done, and let's see here. So it did 500 iterations. Now, you might have noticed that you might ask the question, why was it that it wasn't writing these files to the screen as it was running? Because if you recall in the code itself, down here, it should have written this to the screen, right? Well, the reason why it didn't write to screen is because it buffered it, right? And so the computer knows that the slowest thing it does is I/O, and so it won't always write to the screen every time you give it the write command. It only does it when it's done doing other processes. So it buffers for so long, and I don't know what that buffer is set at, and then once the buffer is full, it dumps it to the screen. So you can go in and set the buffer to 0 within Octave so that it will echo to screen every time you ask it to echo to screen. All right, so it did that, and let's get out of this, and now let's open up that plotting script file that I showed you last time. I made one quick change to it, and that is that I wanted to not open every DAT file, because we don't have every DAT file, right? We only have every 50th one here. So for the loop, I go in and I say start at 0, because I know I'm going to have a 0, and then count by 50 up to this 500, right? And, and then I'm going to do a little trick here where I have a counter, so that this counter is going to index itself right here. So it's going to go from 0, 1, 2, 3, 4, 5, like that. And so then when I create the plot dump files here, I use iCount instead of II. So my PNG files will be sequentially numbered. All right, so let's see how this works. Plot underscore So there's the first iteration, or the 0th iteration, and there's the first. Here's the second. So this is just the evolution of the scheme, and it's not related to the time step at all. And we can see that they're being generated here, these PNG files. And the reason I want them sequentially numbered is that the FF-MPEG routine that I showed you earlier that builds a movie works a little bit better with sequentially numbered files. All right, so there they all are, and they came to screen. It looks like it hasn't converged yet, right? So that does not look like the right solution. And so we're going to have to increase the resolution, or the number of iterations that we do. So let's go up to 2000. I'll save that. Now over here, there's this command called time, and that will ask, or that echoes to screen what the timestamp is. Now that's in seconds past some reference date. So what I can do is, if I said t, let's say start equals time, and then I waited some time here, and then I asked what the difference in that is. It should be a few seconds, right? So it was about 8 seconds. All right, so I can do the same thing when I run this script. I think what I'll do is I'll say t start is equal to time, and then I'll run the script, and then I'll say t stop is equal to time. All right, so there we go. So this is going to take some time to do, almost 4 minutes, I think, to do this. So I will let this run, and then I'll be back when it gets there. So let's see. Yeah, so it's only done this one, right? Oh, I just wrote the 100. I'm looking at the time that it's updated. All right. All right. So it's done. And you can see that when it finished, it did scroll up all of the names. I'm going to hit the space bar here. Okay. So that took some time, right? About 4 or 5 minutes, I think, for that to happen. So that is non-trivial. Now let's look at the results by first plotting them. So let me come in and let me get out of this, and let me edit that plot to increase this from 500 to 2000. And then, yeah, let's check to see how long that actually took. 9 minutes. Wow. That's 9 minutes I'm not getting back, right? Okay. So let's do the plot. Whoops, got to spell it right. So there they are, echoing to screen. It is kind of interesting to watch this converge. It seems that this region converges first, and then it takes a while for the curvature of these streamlines to kind of converge to what we think it should be, right? Looking better. The solution's still changing a lot out here. All right. So there they all are. I'm going to Control W, which closes these. And I'm going to open this window here. And what we can do is I can hit this space bar, and we can kind of scroll through it in more movie-like fashion. So you can tell me if you think this has converged. Still looks like it's changing a little bit. Still seems like it's a little bit of change. Maybe it's not completely converged yet, right? So that's pretty cool. Let's do something else. Let's open the last one here, which is what? Step 40, I think. And so this is our going to be our high resolution run. Let's go over here. That's it right there. This was our low resolution run. And let's open step 40 over here. Now, they're not the same 40, right? On the right, it did 2,000 iterations. So there they are. Now let's look at the difference. So obviously this is a lot coarser, and it appears that Matlab didn't do a good job, or Octave didn't do a good job drawing that corner, interpolating between these points. It drew the interpolation as a line, right, between 2 and 3, so the 0 is actually there, as we saw in the presentation. So don't always believe the plot is the bottom line here. But you can see that it's much smoother than, or much coarser than it is on the right. But I think more importantly, it's a different solution, right? Look at Streamline 4. It's hitting 5. I mean, it's still converging, or this one's converged. This one is still converging, but they are different solutions, or they appear to be very different, right? Especially down here where we're around 2, and the Streamline 1 is quite far away from there. So that is pretty interesting. Now, we'll talk a little bit more about it next time. But so it seems like we still have to converge the solution. We have to converge not only in iterations, but we also have to converge the solution as far as the resolution goes. So the thing to do here would be to converge this in time and then increase the resolution again, the spatial resolution, and redo this to see if we've converged in space. And that technique is called mesh convergence. Did we converge the mesh? If we continuously increase the resolution of the mesh, does the solution change? And so all of these things that we do when we check these are inherent to all CFD kinds of calculations. So you should be suspicious of any kind of CFD calculation that you see someone do, because it takes a lot of effort to get a good solution that you can believe. All right, so I think we'll wrap it up here next time. And what I'll do, wrap it up here this time. And what I'll do next time is do a little fortran. And it's way easier than you think. At this point, to run fortran is a pretty straightforward problem. So I'll show you fortran, and I'll show you how much faster fortran is than Matlab. All right, so we'll see you next time. Bye.